I bet you wasn't recording. That's okay. That's all right. Thank you, sir. I appreciate that. And we're going to come back to this diagram anyway. So the question is, if we have this 12% in the population, can we build an interval around it and then see where our flu vaccine lands? If our flu vaccine lands down here, then we're 95% confident that the flu rate is being lowered. But if it lands up in here, then we're not. Does that make sense? It's where is the test statistic, where, Laura, does your 10.1% land? So in other words, Will, rather than build the confidence interval around the statistic, let's form what should be around the parameter, if you will, the 12%, if-ish. Let's see how wide this should be. Now, that's going to be a sampling distribution. I mean, we have no idea what the original distribution looks like in the population. But the sampling distribution is going to be bell curve. I always draw the bell curves looking like this, no matter what the sample size is. You guys know that if the sample's larger, these bell curves are going to be very tall and very skinny. And if their samples are small, they're going to be very fat and very wide. Okay, or very short and very wide. The question is, without having to draw accurately each time and do calculus, can we rely on the machines to tell us where it lands? We will, but this first one I want to actually crank through manually so you can actually see where it lands, if that's okay. Laura, that's a very long-winded answer to your question, and I apologize, and it's a good question. So we need a third approach, basically, and that's what this actually is. That's what the hypothesis test is. The first thing, though, let's state the hypotheses we're actually going to test. H1 and H0, okay? We're going to come back to this, I promise. We're going to come back to this. Rosie, ask me that question. Are you good?
No, I was
You're good.
know what it says on the board.
Excellent, fantastic. And I'm going to come back and read and word some of this stuff. Apologies for the red marker. Maybe I have one. Oh, hang on. This one writes. Hell yeah! We got a black marker. It's the little things, friends. It's the little things. I'll redraw that curve with black. Now, the first thing it asks us to do is to define the variable and state the hypotheses. What variable are we interested in studying in this data collection, in this sample? What variable are we interested in studying? What do you think? What are we studying? If the flu vaccine actually works. Awesome. So what are we interested in to see if the flu vaccine is actually working? Be brave! Whether they get it or not. This sounds binomial. This sounds binomial. Whether they get it or not. Sounds like a binomial, doesn't it? So we're going to keep track of how many get it, how many don't. Form a ratio. And what's that guy going to be right there? Little p. Little p is going to be the population proportion of those getting the flu with the vaccine in their systems. Because remember, we want to see if the vaccine is effective or ineffective. We have to give them the vaccine to actually see if it's effective or ineffective. Does that make sense? We have to put the vaccine in their body and see what happens in order to see if it's actually doing anything. If we don't put the vaccine in their body, we know the answer already. 12% of the population gets sick every year. We know the answer. There's no reason to use taxpayer money to do a study. It's at 12%. Harrison, that make sense? You got that. Good, very good. The question is, if we inject them with the vaccine, we can study that flu rate and see if that is any different than the general population. Fair enough? Fair enough. Okay, we're the researchers. We're the pharmaceutical company. We collect our data, or better yet, we hire a third party, neutral third party to do it for us, which you should do, correct? All right? And what do we go into the study assuming?
It's not.
We go into the study assuming that it's going to do nothing. What do we go into the study hoping that's going to happen?
Something.
Yeah.
That it's going to be effective. Define effective again.
Less than 5%.
Careful, that's how we're going to measure effectiveness. Define the definition of an effective flu vaccine. I'll get you started.
Less than 12% of people.
Say that again.
Less than 12%
Yes.
of people are going to get sick.
The population proportion of those using the vaccine and getting sick is going to come in at less than 12%. Perfect. And we're going to measure it. You've already given me how we're going to measure it, Cassie. Thank you. We'll measure that in a minute. I promise. There we
So
go.
in reality, even if it helps one person and it makes it 11.99999.
It depends. Say that again, just nice and loud, nice and loud.
So even if it only helps one person and makes it, 11.99999% of people are still getting sick, is that considered effective?
Is that considered effective? Jess Yearls might want to answer this question. Is it significantly statistically less than 12? That depends on your sample. Because as the sample changes, the width of the curve. Can we come back to that question? Because this is where technology really shines. We can mess with the sample sizes and see sometimes that will be statistically significantly different, and sometimes it won't be. It depends on your sample size.
Because it could be the outlier, right?
Exactly, right. And an outlier moves depending on the curve. Depending on the shape of that curve up there. The value that cuts 5% off varies left to right. It'll always be less than 12%. But the question is how far away? Does that make sense? And we'll come back to that. It's a great question. And it's what Jesse was talking about a couple weeks ago. It's a fantastic question. It depends on your sample size. But for a sample size of 1,000, it's a fixed value. We're going to figure out which side of that we're on.
Okay.
Thank you for that. It's very, very good. Now, friends, that's what we're hoping as researchers. What's the mathematical opposite of that? Greater than or equal to. The mathematical opposite of that would be the people that are on the vaccine are going to either get sick at the same rate as the people that don't on the vaccine, or worse, they're going to get sick more frequently. That's the absolute opposite of the research hypothesis. Now, I have no problem with you writing it like that. I still kind of write it like that because that's how I was taught. But since I was in school, this has become acceptable to just write that as P equals 12%. If for some reason the inequality signs have been dropped off, I know, Laura, I see your brow furrowing. I don't like it either. I like the mathematical opposite. If this is what we're testing, that's the mathematical opposite of it. And the reason I like this versus that is that that implies the whole other side of the curve over here. Equal to or greater than. When you don't write that, your mind might inadvertently chop this tail off and say that's not important anymore. It is. It's just convention that they write it this way. It still implies this. What am I trying to say here? Write it either way you want to. Doesn't matter to me. The important thing is you get this one correct. Go, Danny.
I don't know if it's relevant at this point, but our parameter was 11.97%.
Our parameter.
On the margin, the confidence interval, sorry.
Oh, as opposed to 12?
Yeah.
Don't worry about that. Danielle's referring to the confidence interval Will calculated for us before. That was the high end of the parameter, right? We're going to build a different interval around the 12%, not the 10.1%. So in other words, we're going to let the 10.1% be a point estimate and see where it falls on that curve, in or out. So don't even worry about that anymore. We'll come back to that. The idea is a confidence interval is a fantastic way of estimating a parameter's value. But to estimate change, this one-sided interval does a pretty good job too. And it's the third attack. You're not convinced of that, Laura, that's good. We'll come back. We'll come back. So here's your hypotheses we're going to be testing. The idea now is, do we believe this or do we believe that? If we believe that, that means the flu vaccine appears to be working. If we believe this, it's back to the drawing board and try some new composition of your flu vaccine and try again. If you have enough funding to do so. Fair enough? Okay. Next step. Collect your data. I call this step 1.5 because this is actually the hardest thing to do, in all honesty. This is why our entire course is devoted to research methods, because you actually have to go out and get your data and then process it. But getting the data, I mean, think about it. I just handed you 4 pages worth of data, and we're going to collect more in class. This represents 6 weeks what we're going to be doing in class. If I made you go out and collect all this data, plus what we're going to collect in class, we'd be collecting data for like 18 straight weeks. Which might be fun, until it's snowing outside, and then it's not much fun. Okay, step 2. Cassie, we're finally getting around to your question. Okay, less than 5%. I don't know if it's less than 5%. I have to figure out if it's here or if it's here. And here is where your 243 and your 244 shake hands. I'm going to adjust this curve a little tiny bit. Okay? That 5% is perfect. I'm going to redraw this so the red jumps out. Okay. Now, here's the deal. This stands for the 12% that usually get sick in the general population. What I want to do is be able to turn this, as opposed to talking about a bell curve that's centered on 12%, I want to talk about a bell curve that's centered on 0, the number 0. Remember him from 243? We called him the standard normal curve, the standard normal distribution. That's what we care about. We care about that because any bell curve can be normalized down to 0. Any bell curve can be normalized down to 0. Fair enough so far? You guys buying this? Okay, fantastic. So the question is, I can get a p hat value from my sample, and we already have. Okay? The problem is, I don't know if p hat is over here or if it's over here. It's clearly to the left of 12%, as Lars pointed out, 10.1%. The question is, I don't know how far it is. Is it here or is it here? So the question is, rather than dealing with that 10.1%, let's deal instead with what's called a test statistic. And what a test statistic's job is to do, I'm going to mute this for a second. A test statistic is a way of measuring how far deviant you are from your expected value. Okay, I'm going to swing back over here. We're going to use this board right here. Back out a little tiny bit. Now this definition of a test statistic, we're going to use this forever. And it's going to look familiar. It's going to look familiar to you. A test statistic. Harrison, is that thing still recording?
Yeah.
I think I should try to hit record the first time. Okay. A test statistic looks a lot like a z-score. Remember those from 243? Here's why. Your test statistic always is of this-ish form. And I say ish because it has to change a little bit depending on what we're testing, but it basically does this comparison. Your test statistic, boom, boom, is going to be equal to your sample's center minus your population's assumed center. Leave some space under that, we're not done yet. What will that give you right now? What does that give you right now?
1.9.
Yes, negative, correct? Negative 1.9. How did we get negative 1.9 from that? 1.9%, correct? Negative 1.9%. What was your sample center? 101 out of 1,000, Chloe, thank you. 101 out of 1,000 is 0.101. What's the assumed flu rate? Assuming the vaccine is ineffective? 12%, 0.12. 0.101 minus 0.12 is negative 0.109, right? There we go. 0.019, there we go. 1.9%, and it's negative because it's lower. Fair enough? But that's just the percentile point difference between 10.1% and 12%. This goes back to Kaylee's question. Is that significant? Well, all that tells us is the distance from here to here is negative 0.019. How can we tell if that's significant or not? How do we know if it's here, or if it's here, or if it's here, or if it's here, or if it's here? Let me ask you a different question. If it's here, is the flu vaccine working?
No.
If it's here, is the flu vaccine working? Yes or no? Yes or no?
No.
I hear a vote for no. A very strong vote for no, actually. Will, why not?
It's not in that 5%.
Harrison, would you swing that camera pointing over here, if you don't mind? Or Kaylee, if you don't mind, thanks. So if my test statistic, if my P hat is 10.1%, and it lands right here, it's not statistically significantly lower because, Will,
Inside that 95%.
you're still in this 95% confidence interval around 12%. What if it's right here? Is it significant? No. Danielle's saying no for the same reason. What about right here? How about right here? If it's out here, somewhere out here, then we know it's statistically significantly different. So here's the question I have for you guys. It's 10.1%, regardless of whether it's here, 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 or here. I feel like Bill Cosby. Here, 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 here. How do we know where it is? What else do we have to calculate? What else haven't we even talked about?
Standard deviation.
Listen loud, Will.
Standard deviation.
The standard error in the sample is okay. I love that you said standard deviation because you mean the spread. How far is that? What? Remember, what is a 95% confidence interval, basically? Say this aloud, Cassie, more.
2 standard deviations.
2 standard deviations or 2 standard errors away from the average, correct? So you have to know how far out 2 standard errors is. Why does that depend on sample, Kaylee? I mentioned it depended on sample. Because if your sample goes up, what happens to your standard error?
Goes smaller.
Yes, it shrinks, it gets smaller. So that's what we have to calculate. We have to divide this by the standard error of the sampling distribution. Come back up front with the camera. I apologize, you guys. I should put that GPS chip in my pocket one of these days. We have to figure out what the standard error is. Once we have the standard error, we essentially have a distance on the curve. And if we divide that distance into our raw distance of negative 1.9%, it tells us how many standard errors we go out. And if we know how many standard errors we go out, we'll know if we're in or out of the confidence interval, won't we? See what I'm getting at here? We're essentially building the interval backwards. We have our test statistic, and instead of looking at the margin of error, we're looking at a standard error, a single standard error, and seeing how many of them we go out. And if we go out far enough, that means we're statistically significant. Yeah? Good. Now this is a little bit goofy. The way you calculate this is a little bit strange. It's a square root. This is the one and only time we'll do this, by the way, just so you know. It's a square root of, and it's going to look a little bit familiar. For this particular example, it's going to be 0.12 times 0.88 all over 1,000. Who wants to hazard a guess as to why the hell it's that? Who wants to hazard a guess as to why the hell it's 0.12 times 0.88 over 1,000? Rosie, go, my friend!
Didn't that, but I can't remember the word for
Mhm.
it from 243, but
I see your pen going back and forth like this, and that means you're complementary ideas. Where's the 0.12? He should look familiar.
Infection rate.
Yes! That's the assumed infection rate. What's 0.88? The people who didn't get infected, the complement, that's why I saw the pen going back and forth, I know what you're doing. What's 1,000? Why are we using 0.12 and 0.88? Not that you have to memorize this, but we're using that because when we go into the study, what are we assuming?
Nothing's changed.
That the vaccine is ineffective, nothing's changed. So we're basing the standard error, this goes back to our curve. We're building the standard error around the fact that 0 has changed, nothing has changed. Yeah? Please keep in mind, friends, this is the one and only time we'll calculate one of these things manually. Okay, just so you know, I want you to see the construction of it to see where it comes from. But it's the one and only time we'll do it. We're gonna let the machines do it for us, almost inevitably. Because I don't want you to get hung up on this mathematics. Okay? Laura, ask me that question unless you don't have one. Maybe.
Oh, no, just the 1,000 is just from the sample.
The sample, exactly. Because even over a sample of 1,000 people, we're still expecting 12% of them to get sick. Fair enough? Okay, let's crunch this real quick. So we get here 0.12 times 0.88, divide by 1,000, which is dumb because I'm making square root of that. I get about a 0.0103-ish, somewhere in there. Are we getting the same thing? That's for the standard error. So this is going to be negative 0.019 divided by approximately 0.0102-ish. You getting that? Ish, somewhere in that neighborhood. Ish. You guys with me? That's standard error, and that's also a percentage. So this means that our standard error of our sample is about 1%. So remember how our margin of error is often 3 and 4%? This is much smaller, 1%. Probably because of the sample size of 1,000 versus sample size of 500, things like that. Okay? So now what I'm going to do is I'm going to do a real quick calculation. I'm going to do this guy divided by this guy and see what I get. Okay? All right, here we go. I'm going to do negative 0.019 divided by that mess. And I end up with about negative 1.85. That's what I'm getting. What the hell is that? What the hell is that thing? Negative 1.85. What the hell is that? I'll give you a hint. When you take a sample average, subtract the population average, and divide it by a standard deviation, that should sound like something from 243. Back in the day, we did an x bar minus mu over a standard deviation. Remember what we called that back in 243? What letter did we call that? We called it normalizing or standardizing data. I used Michael Phelps and Mark Spitz to introduce this idea back in 243. I don't know if you guys did that for 243, you didn't see that. But what were we doing? We were turning data into what kind of data? And placing it on what kind of curve? Look behind me, over here. Bell curve, what variable did we use to talk about the first bell curve we ever talked about? Do you remember? Maybe you don't remember. That's okay if you don't remember. It's a z-score. So this is a z. At the end of the day, it's a z-score. It's a z-score. And that z has a place over there. That z has a place over there. So I'm going to swing over here again. Zoom in on that curve. We're going to come back. So right now, the test statistic for our data is z negative 1.85. Z is negative 1.85. Negative 1.85 what? What? How many blah below blah?
Is it standard deviation?
Yes! It's how many standard deviations below mu, below the average. Yes, you guys got this. You be brave. You got this. You know what this is. It's how many standard deviations down we've gone. We started at 0, and we have dropped 1.85 standard deviations. Now, some of you go, okay, we dropped 1.85 standard deviations. That's not significant because it's not what? It's not 2, correct? Here's where you have to let your mind wander a little bit. It doesn't have to be 2 unless the interval is two-sided. Remember what we did with a one-sided interval? With a two-sided interval, you put here, and it's 2 down and 2 up. But if it's a one-sided interval, you take this area over here and you shove it on this side, which actually pushes this up a bit and makes it not all the way down to negative 2. The question I have is negative 1.85 far enough down? Well, that requires step 3. Let's come back to this. You can't see that? Now you can. Here, back out. Step 3 is take your test statistic and figure out the marvelous p-value that goes along with it. Figure out the p-value that goes along with it. And here comes the only time we're going to have to figure this out old school. The only time to figure this out old school. And when I say old school, I mean 243-ish. Okay? The only thing I'm talking about when I'm talking about 243. Okay? That test statistic, now that it's z equals negative 1.85, we now know this thing lives on the bell curve. If it lives on the bell curve and it's got a value, we can find the area that goes with it. That's what we're going to do next. Put that down, swing the camera over again. How much you think it would be to get a film crew in here? Like makeup artists. You know, the whole shebang. Catered. Groupies. kind of
Roadies. Oh my god.
roadies. We're talking about roadies, big trucks, sponsorships, which we get like 5-hour interview with you on board. Anyway, here's what we're gonna do. You see all this right here? This is all fantastic. I'm gonna erase all this. This is what I care about. You know, I'm gonna erase this too. I'm gonna erase this too momentarily. We're gonna put that 5% back up in a minute. But what I want to do right now is, I'm going to place the only thing I know about right here. And that's z equals negative 1.85. That's what we just turned our data. Your data can always be turned into a test statistic, and I'm always going to ask you to do that. Here's a bunch of data, here's a sample size, here are the results. What test statistic pops out? Your job is to calculate that test statistic's p-value. I really wish I had it. Oh, perfect, here we go. So here's the p-value. The p-value, because purple starts with p, is I want you guys to figure out what that area is right there. Now what that area is the p-value. That's the chance, assuming that the flu rate is still at 12%, it's the chance that we got our lowered data. It's the chance that we did get lower data, right? We got lower data, we got 10.1%. But the question is, was that coincidence? Or is the flu rate actually at 10.1% or lower? What's the chance of that happening, assuming the flu rate should be at 12%? Can we figure out what this area is right here? You can say yes. You can also say no if you forgot. If you had me in 243, I gave you a program called Normal. If you had me. And we can use that right now. One and only one time. Don't worry about it. You're not going to need a Rosie. That's what it'll come out. It's okay. If you don't have Normal, just stick with me for a second. Get the calculation. You don't need it past this particular example because your TIs have built-ins. So up to the front board, we're going to show you how to calculate this bad boy. There we go. Let's back this out. That's in. Okay, let's fire this up. See it? If you don't have Normal, don't worry. If you don't have Normal, actually, you did it using tables, I'm sure. So if you had Donna and used tables, you'll just have to call on those memories. Slide this down a little bit. How's that look, friends? Is that ish centered? Is it decent? Mm-hmm. Ish. You can zoom in if you want. Actually, let me do this. Okay, go ahead. You be my roadie. It's strictly a volunteer gig. I apologize. Give you 100% of my profits.
Okay.
So here we go. If you still have the programs I gave you, it's under Program. It's called Normal. If you don't have this, don't sweat it. You won't need it more than this one time. Okay? If you had me in 243, do you remember what kind of problem this is?
I can't remember.
It's okay if you don't remember.
I guess it'll be backwards.
It's actually a forwards problem because you have the z-score. Backwards problems, you have the area. I can redo this one. We'll come back to that. It's a forwards problem. Which way is the area shading? It is definitely shading to the left because we're trying to see if the flu is being decreased by the vaccine. So we're trying to ask ourselves, here's the formal definition of a p-value, set a geometric way. The results we saw in our sample, 10.1%. What's the chance of getting those results or even more flu reduction? That's what we care about, right? More flu reduction, not necessarily less reduction or increase. We want to see decreases. So we're going to go area left. The right bound would be the value that we got, the negative 1.85. When you hit enter, it will now draw you the curve. Here she comes. There's the area. There's the same picture we have up there. Look at the area. 3.22%. Purple. That's your p-value. The p-value is that area. So in the last homework assignment, when you were looking at p is less than 1%, p is greater than 5%, p equals 0.23, all that stuff, that's how they got those numbers. They were slapping their data, nicely of course, keep it coming back, but they were putting that data up onto a curve and seeing how much area was in any given tail. How much area was in any given tail. So I'm going to swing over here. So you can see this. We'll come back to that momentarily, I promise you. Zoom in on it a little bit. Okay, here we go. So now this, friends, your p-value, and like I said, I'm going to be real careful about when I write this stuff down. P, big P. Your TI sucks at this, just so you know. Big P, 3.2%, otherwise known as 0.032, otherwise known as less than 5%. Otherwise known as less than 5%. We're finally answering your question, Laura, an hour later. I apologize, it took an hour. What do we think about this flu vaccine? That was a very lukewarm vote for it. It works.
Well, there's no question.
Go ahead, Rosie, say it brave. It works! How can we tell it works? And of course we're saying this with 95% confidence, not 100% confidence. We're basing it off our sample. How can we say it works?
Less than 5%.
Because the p-value is less than 5%. Give me more. I love that. Thank you guys. I love that. Give me more. What does the p-value being less than 5% mean? I'm going to say it to you, ass backwards. It doesn't appear that it's not working. How does that answer the entire question right there? Which hypothesis are you believing? When the p-value is small, which one do you believe? You believe H1. These are your hypotheses. When the p-value is small, you believe this one. Why do you believe this one when the p-value is small?
Statistically significant?
Yes, how come? I love that. It's statistically significant. How come? And I'm not picking on just Cassie. I'm asking everybody. Cassie, you can jump out if you want. Go ahead and tell me if you want. I'm asking everybody. Why do you believe H1 when your p-value is small? And I can answer this ass backwards for you again.
It disproves what you originally went with?
I try to say it a different way. I love what you just said.
Absolutely.
It's too hard to believe this. It's too hard to believe this, so it's easier to believe this. Cassie, you said it. I just don't like that with the word disprove. I get nervous with the word prove with statistics because we haven't proven one or the other. We're just saying it's hard to believe this. It's easier to believe this. And here's why. This goes back to Laura's question. We're assuming the vaccine is doing nothing. We're assuming the vaccine is doing nothing, which means that at a 12% infection rate, that's the general population, 12%. We got 10.1%. Now the question is, what cutoff? What cutoff? And clearly we know where it is now. It's got to be over here somewhere. Somewhere right there is the lowest possible flu infection rate that we could get and feel good about saying, you know what, the vaccine, sure, it dropped it down to 11% or 12% or 11% or 11.1%, but that's still close enough to 12% to say, it's still too close to say anything's working. Somewhere, though, there is a cutoff called a critical value. We've talked about those before. Somewhere it's called a critical value. If we get past that critical value, this area right here, all this area right here is 5%. So in other words, what we've essentially done with that question mark is we've set up a 95% confidence interval around the 12% and said if our sample data lands in that 95% confidence interval, we believe this. In other words, we believe that the flu vaccine is doing nothing. There's no reason to think that the flu rate has been lowered. If you think of it in statistical terms as you have failed to reject the null hypothesis. Very stuffy pipe. It's a chair by the fireplace, robe. You fail to reject the null. That's if you land in this interval. Well, how are you going to know if you land in this interval? What's your p-value going to come back at? More than 5%. 6, 7, 8, 9, 10, 45, something, but more than 5. Fair enough? That's how you know you're in here. Were we in there with our sample data? No, our sample data put us at 3.22%, which put us over here in the tail. This is why I rephrased what you said, Cassie. It's hard to believe this, because in order to believe this, I'd feel better about our data being in here, but our data actually landed out here in the outlier tails. So either the flu rate has not been changed and we got bad data, when I say bad I mean outlier data, or the flu vaccine's actually working and we saw typical data for a lowered curve. In other words, there's most likely a curve somewhere over here that represents lowered flu rates, and we're on that one, rather than being on the normal flu rate curve. How far down is our lowered flu rate curve? Trick question. How far down is our lowered flu rate curve? We don't know. We're just going to make the claim that it looks like it's statistically significantly further down. And that's all we were testing. All we were testing was that it was less than 12%. If somebody demands to know how much further down, well, this is where you build your interval. Then you build your interval and say, here, boom, it's minimally this far down. Then you build the interval. But this is just testing to see if there's a difference off the bat. Does that make sense? That's how we came full circle to that? Yeah, two different questions. Has it changed? If so, how much? Is that good? You guys buy that? So there's your conclusion. That's step 4. Let's swing back up to the front board here, and then I'm going to show you a shortcut so you never ever have to go through that math again. Because I don't want you getting hung up on the math. I really don't. I'm sorry, I'm doing your job for you, Kaylee. Yeah, I figured you wouldn't mind. Straighten her up. Step 4. State a clear, concise, correct, contextual conclusion that someone who has never taken a statistics class will understand. As I said, you could say,
I reject the null hypothesis. I support H1.
You can say these things all day long. But imagine you're trimming your bushes, talking to your neighbor across the fence. You're both out there cutting the lawn, pulling weeds, getting the last bits of kale out of your garden for the season before it freezes. And your friend says, you know, I got my flu shot last week. And you say, oh, that's good. And he says, well, why? Why is it good? I mean, I've heard people get sick when they get flu shots. And you go, yeah, but you rejected all hypothesis. No, you said it's been statistically significantly shown that the flu rate is lowered when you get your flu vaccine. Will your neighbor understand that? Maybe not the statistically significant part, but will he understand it got lowered? Totally understand that. So you can say something along the lines of, it appears as though the flu rate has been significantly lowered on the vaccine. Not by how much, can't say that just yet, but just say it's been lowered. The p-value came in below 5% of our sample data. Could we be wrong? Yeah. Of course we could be wrong, right? What kind of error could we make in this case? What type of error could we make in this case? Type 1. Vote for type 1. Do we have a second for type 1? We could make a type 1. Jack's got a second. All in favor? 2 in favor. Ooh, good. How do we know it's a type 1 potential? Because you got a small p-value. You got a small p-value, acted appropriately. Small p-value means you say something's changed. It's too hard to believe H0, so you believe H1. H1 said something changed. So the type 1 error would be a false, that'd be a false positive, right? Which means you said the flu vaccine is working, when in fact, it wasn't. Which means you landed in that tail of the bell curve, correct? But you landed in the bell curve in that weird 5% of the time when you still belong on that bell curve. That big black bell curve that I drew. You belong on that one. But you landed out there as an outlier, not as a deviant data point from some other data set. That's a type 1 error. We'll come back to more of that on Thursday. What I want to do first, or next, I guess, is show you a much easier way to get these values and focus on the interpretations. We spent a lot of time today calculating test statistics and then also figuring out where the hell they sit on that curve. So as a finale today, let's show you how to get all this in your machines and also focus more starting on Thursday on the interpretations of what the results mean. So work with me here, Let's swing this guy over a little bit more. Yes, let's mute the screen, grab your TIs. Everybody now, this is not a program, this is a built-in. Danielle, this is going to be under menu F6 versus F7 for you, under tests instead of intervals. All right, let's fire this up. Is that pretty visible in the screen-ish? Oh, thank you. I gotta get you a cut of the profits. With me? Okay. Stat. Oops, gotta quit the program first. Stat tests. The one you want to use is called 1 prop z test, and you can see them right there. That sounds like 1 prop z int, and it's exactly the it's essentially the corollary to that, but it lets us set up a 1-tailed test as well as 2-tailed tests if we need to. 1 prop z test, here we go. Our job now is to fill this in. Some of this looks familiar, doesn't it? Some of this looks familiar. X and N looks familiar. And X and N would be exactly what it would be before, 101 out of 1,000. As a matter of fact, it's called in my numbers that I entered in before, because it's kind of like that. There are two different things. There are two different things. P sub 0 up here. That's the percentage in the null hypothesis. So what you have to do, and this is why I make you write it down, is you have to go back to your null hypothesis and put in that percentage. In this case, 0.12. 12%, 0.12. Whoops, 12. Is that fair? Is that fine? Down here, you have to put the correct sign in your research hypothesis. I wish that TI used more standard language for this. But this proportion is you have to pick one of these three signs. And this is, again, why I make you write the hypotheses down. Your research hypothesis is a less than, so you're going to go ahead and pick less than. And if you follow along the kind of flow of the symbols, what's the chance the proportion is less than P naught, and P naught is 0.12? That's exactly what is written in H1, isn't it? It's TIEs, and you'll get used to this. It's TIEs, and you'll get used to it. Two choices now. You can calculate it or draw it. I like drawing it, personally. I like drawing it. And this might look familiar to you. Does that look familiar to you? Look familiar?
Little British right there.
Does it look familiar? Yes! It's the same p-value that I calculated for you using normal. But it doesn't. This is why I told you you don't have to have still normal. Make sure you pick the correct sign. You pick the two-tailed. So when you run that test, when it's at prop, the first choice is does not equal P0. You left it on that one. You have to switch it over to less than, strictly less than. So this is nice. It gives you your test statistic right there. It also gives you the p-value of that test statistic. Then you can focus just on your conclusion. Oh, it's less than 5%. That means something's changed. What has changed? It must be that the flu rate has been lowered. That's what you were looking for. It doesn't tell you how much. It just tells you that it's been lowered. That's all we're working on right now is, has it been lowered? Yes? Yes. Feels kind of squirrely, doesn't it? A little squirrely? Laura, that was like an hour and a half answer to your question. I apologize. Sometimes it takes an hour and a half. But they won't take an hour and a half for the next time because now we know the process. It's get the hypotheses, get the test statistic, get the p-value, and put it all together into one statement. That's what we're going to do for the next 6 weeks together. Just looking at different kinds of data. Do you have one data set? Do you have two? Do you have four? Are you testing proportions? Are you testing averages? Is it discrete? Is it continuous? It all boils down to 4 steps. It all boils down to 4 steps. The question is, which test statistic are we going to end up using? That's what we spend the next 6 weeks talking about. Yeah? Get the hell out of here. Go do your test corrections.
What's DIM?
Harrison, say again?
DIM.
You got a dim mismatch?
It's invalid.
Invalid dim. You've got a